Hello, everyone. Welcome to the Combustion webinar. I'm Wang Han from the University of Edinburgh. Today, our speaker is Professor Thierry Poinsot. It's my pleasure to introduce him. Professor Poinsot is a research director in CNRS, head of CFD group at CERFACS, and the senior research fellow at Stanford University, also a consultant for various companies. Last December, he was elected as a member of French Academy of Science. This is a great recognition for his work over the last 30 years in combustion CFD and instability in real engines, since he received his PhD in 1983 from École Centrale Paris. He has authored more than 200 papers in journals and is also textbook theoretical and numerical combustion with Dr. Daniel Veynante and the editor-in-chief of General Combustion and Flame with Professor Egolfopoulos. He has received many academic awards, such as the Aldrich Gold Medal from the International Combustion Institute, a first ERC advanced grant in 2030 on thermoacoustics, and the second one last year on hydrogen combustion for energy storage. Besides, he teaches numerical methods of combustion in many schools and universities in the world, and has an elegant and informative teaching style, which I'm sure you will appreciate as he delivers today's talk with title Simulation and Control of Renewable Combustion. Professor Poinsot, we can start, please.
Okay, thank you very much for this very nice introduction. I'm not sure if it is good morning or good afternoon or good evening, but hello to all of you, and I will spend the next 40 or 45 minutes discussing the simulation and the control of renewable combustion, basically a lot of it being on hydrogen. So before I start talking about combustion itself, I would just like to discuss energy first. And to do that, I would like to introduce a concept to count energy, which is discussed in France by a guy called Jean Covici, who is really working on these issues. And Jean Covici introduced this number called the N number, and the N number quantifies how many people are working to provide your energy. So, you know, a few hundred years ago, people were using this kind of energy, and that was fully renewable, by the way, but it was not much, you know, and actually, if you want to count energy as the number of people working for you full-time, maybe here you would have N equal 2, you know, because these animals don't work for the whole day, they need to sleep, etc., etc. An interesting question is that today we have replaced these animals by machines. And an interesting question is, do you know what this number N is today? You know, how many other human beings are actually working to provide your energy? This number is actually amazing. In the world, on average, it's 200. It's about 600 in France and more than 1,000 in the US. That means day and night, each of us has at least 200 slaves working for him full-time to provide his energy. And the next important step here is that this energy is provided by combustion, okay? And that's something, of course, that the public ignores, but that we know in this community. We know that more than 90% of the energy produced on Earth is obtained by burning something. And the examples, of course, are numerous. It's good to remember that it means that on average, each of us burns like 2 liters of oil every day, which is amazing when you consider that a lot of people don't drive cars, but others have 2, 3, or 4 cars. And why do we do that? Well, we do that because the heat release for every kilogram of fuel that we burn is enormous. For most hydrocarbons, as you know, Q is of the order of 50 megajoules per kilogram. And that's much more, for example, than batteries. You can store much more energy in 1 kilogram of kerosene that you can in 40 kilograms of batteries. So the next equation in this talk is that this is not going to change, okay? The energy on Earth tomorrow will also be combustion. Why is that so? Well, it's, if you compare here, the energy produced in 2010 to the energy planned for 2035, which is the additional blue zone here, you see that you're going to increase renewables by an enormous amount, like a factor of 2. But the global need for energy is also pretty big, so that we will need to burn more and more. If you look actually at the details of what we burn, you have here the wood over time from 1860 to today. And you see that the wood was more or less renewable, but it was not enough. So we added coal, and coal was really needed and used for produce electricity, and that's still the case today. Then we added oil, and oil is mainly used to transportation. And then we added gas, and gas can do a little bit of everything. Then we added hydroelectricity, the blue line here. And then we added nuclear, and then we added renewables. And you know, the renewables are here. And this is this small zone here, which makes everyone excited, but don't forget that the rest is here, and it's combustion. So today, it's mainly clear that our civilization relies on combustion. So that when you look at the total energy, for example, in 2016, and you look at the share of each part here, so the fossil fuel, the nuclear, and the renewable, and you realize that in the renewable, actually, largest part is also burning waste. And biofuels, you end up with something like 91%, and this number is not going down. So it says fair to say that for our world, consumption of energy through combustion is like a drug. And of course, like most substances, there's a cost to that. The cost, of course, is pollution, but not only pollution through the gases we don't want, it's also global warming. And global warming, we know that there are a few people in this world who do not believe in global warming, but I would say that if you're a scientific person, I don't see how you can not agree, for example, with this very nice talk by Bob Sawyer at the symposium discussing these questions. And it's clear that it's a simple problem. You put CO2 in the atmosphere because of radiation, it leads to global warming, and the CO2 comes from combustion. It was guessed by Fourier 200 years ago, and Arrhenius, actually quite famous people in our field, did actually the first computation. He said doubling CO2 would raise Earth's temperature by 5 degrees. So there is no discussion that it's our fault. Okay. It's not the only way we increase temperature. Contrails also change the number of clouds in the sky, and that also contributes to changes in the climate. So the situation is the following. We burn a lot today, we will keep burning a lot tomorrow, and combustion science has a huge place here. We must do that without wasting fuel, increasing pollution, killing people, or changing the climate. We do our job. You know, if you look here at the evolution of the fuel burn in an aircraft engine, over the last 50 years, we were able to diminish that by a factor of 2, which is enormous, which leads actually to a decrease of a factor of 4 for the aircraft fuel burn per seat. So that's an amazing progress, but still, it's probably not enough for the future. So on the long term, we must minimize fossil fuel combustion. But how do we do that? Of course, we need to go to renewable energies. Everyone sees that. The problem is that these energies are intermittent. You cannot rely on them. You don't know when they will produce. And so the only way to handle the situation where when we will have like 80% of renewable is storage. So we need to store energy. And interestingly, how can we store energy? Well, with combustion again. Those are strategies called power to X to power. And the idea here is to use this excess renewable energy produced by sun or wind to produce a gas, and then to burn the gas when you need it. A very simple example is here. You have too much sun or too much wind. So you do electrolysis of water and you get some H2, and you can store the H2 in the tank and keep it for as long as you want. Now, a little bit later, or the year later, you can take this H2 and burn it in a fuel cell in a car. You could also convert it to CH4 or NH3 for transportation. You can store it in liquid hydrogen carrier, but you could also burn it directly. You could burn it in a piston engine. Actually, a piston engine burning hydrogen will cost about 10 times less than a fuel cell. So in terms of industry applications, more and more companies are looking at hydrogen engines using piston engines. You could actually burn it in a turbine. I will talk about it today. You could burn it in a furnace, of course. You could burn it to make your coffee. Okay, you can do what you want once you have hydrogen. So in practice, it would work like this. You produce hydrogen when you have too much power, and then when you need it, you just burn it in a combustor again. So we're back into business. Okay, combustion again here is not the problem. Combustion becomes the solution. Now, why is it interesting? If you plot here in log scale, the amount of power that you can store with a given device and the time you can keep this energy, you see that batteries are here. And actually, the largest battery today, the battery plant of Tesla is here. But this is like, it's like a toy compared to how much energy you can store just by putting it in a big tank for hydrogen or for natural gas here. So if you want to be serious about storing energy, you need to go to these power to gas strategies because they will allow you to store enormous amounts of energy, unlike batteries. Because if you want to go from here to here with 6 orders of magnitude, we will have batteries everywhere, and that will be a major problem. It's not even here a problem, of electric car that we are discussing. We are discussing amounts of energies which are much, much larger. Well, let's go back to science. Okay, now if we accept that there is a path here for hydrogen, you know that if you work in combustion, there are different problems with hydrogen. Hydrogen leaks, hydrogen ignites extremely well, hydrogen burns extremely fast, and hydrogen explodes. That's a lot of small problems. Flammability limits first. Those are the lean and the rich flammability limit for different gases, and you recognize that hydrogen ignites extremely well, okay? So in terms of safety, it is a problem. In terms of designing engines, those are flame speed for fuel air flame. You see methane here with the famous maximum of 40 centimeters per second or 38 here. But you see that when you add hydrogen, you go up here to maybe 3 meters per second when you go to pure H2. So of course, that means that if you take an existing system and you want to replace methane by hydrogen, you will have surprises. The other problem, of course, is if hydrogen leaks easily, for example, in a building, and you start accumulating hydrogen at one place and someone is smoking or switching a light, then you can have an explosion. Explosions come in different ways. This is an example of deflagration where things are not too bad. But you can have much worse problems, and hydrogen makes them actually very bad. Like an explosion with hydrogen would produce pressures which are like 4 times larger than an explosion with methane. Here in this situation, it's not only the flame propagating in the building, it's the whole building being blown up. And so that's, of course, much more dangerous. And if we go to hydrogen, we'll need to handle these situations. So this means that in practice, since the flames with hydrogen are much faster, you cannot directly mix hydrogen. That's what we call the drop-in strategy by adding hydrogen to methane. You can do that up to a level of maybe 10 to 15%, but afterwards, you will have a problem. So if you want to use large amounts of hydrogen, you need to change the chambers. So that's something which is very well known for cars. It's that at some point you need to adapt your system to the fuel you want to burn. And of course, I've mentioned it, safety becomes an issue. It's not necessarily a bad issue for hydrogen because, for example, in the plane, most experts recognize that a fire in an H2 plane may probably not be worse than a fire with kerosene. Now, the idea is the following now. We can burn H2 in many ways. But for combustion experts, having H2 available and mixing it with other fuel is a waste. Why don't we use the power of H2 to do other things? For example, since we will need to redesign existing chambers, we can do 2 things at the same time now. We could consume the H2, but use H2 to burn fossil fuel more efficiently. Not only to burn H2 itself, because we know that in many cases, we will actually burn H2 with other fuels. What could we do? Here I want to focus on gas turbines. Gas turbines still have a lot of problems. I want to discuss 3 of them: ignition, quenching, and instabilities. Ignition of combustion chambers, of course, is necessary, but it can fail. For example, in an helicopter at high altitude, it can be quite difficult to ignite. And of course, ignition can also be violent in a rocket engine, for example, and lead to the explosion of the engine. That's a view of an ignition in an engine. So this one is a successful ignition, but it's not always successful. So it's something that a lot of people are working on. This is an experiment here in École Centrale in Paris. And this is a simulation. The important thing to remember is that if you have a fuel, which is difficult to ignite, but if you have hydrogen, then you can just add hydrogen for a few milliseconds. It will be like igniting your barbecue, okay? It will make things much easier to ignite. So having a little bit of hydrogen on board could help you in terms of difficult ignition. Quenching is about the same. An engine can quench suddenly, and of course, it's not a good idea. It's a major design issue. And if you have hydrogen, the same H2 bottle you use for ignition, you could also use it if you want to be sure that your engine does not quench in a critical, for example, very lean moment. Instabilities is another problem. We know that many combustion chambers have this bad idea of becoming unstable because they get coupled with the acoustics of the chamber. There are quite a few recent work and also old work on that. I've listed a few of them here on the screen. Just a recent example, that's a last year experiment by James Dawson at NTNU. This is a swirler which should look like this actually, and this is what he found after some combustion instabilities. So you see that combustion instabilities are not only noise, okay? They can just kill your chamber because here, for example, he had flashback. So why do we have instabilities? Well, because we know that flames produce noise. So this is an example here of a flame front, which is the white zone here. And you will see that every time a flame surface is created or deleted, you have emissions here of noise. This is dilatation that you see here. And you see that flame movements create noise. So when the flame moves, it makes noise. And on the other hand, we should take a flame now and you send noise to this flame, then you can modify the flame. That's also a very famous movie by École Centrale, where you see how the flame moves when it's submitted to music.
This time for Africa.
Now, as you saw just now, you can also send music to the flame. It's fun, but it shows you that basically flames react to noise. Now, if flames react to noise, if noise reacts to flames, you have the possibility of having this loop here. And when this loop is closed, then you go into problems like this one here. So that's a combustion instability. And when it happens, you're basically in trouble. We understand most of this stuff, and we know it's due to coupling between acoustic waves and flames. But basically, if you change the flame, you can enter into this kind of regime here where you see the flame oscillating a lot, even going to moments where the inlet velocity in a burner could become negative. So the burn gases are leaving the burner by the inlet, which is, of course, a very bad idea. And all these things have to be avoided. So now, just a few other examples of such flames. You can have instabilities a little bit everywhere. That's a fun experiment that was done also at EM2C. Or another one. All these things happen when you start playing with flames. And when they happen, things can get really bad, and it happens in real engines. And in a real engine, like liquid rocket engines here, it will kill the engine in a few milliseconds. And the most famous example of such problem was the F1 engine in the Apollo project, where this big engine, there were 5 of them here, these big engines were unstable, and they were giving a lot of problems in terms of design. This is actually probably the largest combustion program ever, which was performed. You have here a number which is just amazing for those of you doing experiments. In 2 years, NASA had to run more than 1,000 full engine tests, adding baffles, modifying the shape of the injectors, playing with all kinds of shapes to try to minimize the pressure oscillation. Actually, this is, there are famous papers on that by Offline and Young who summarized this thing. And it was an amazing project. And everything in this project was caused by combustion instabilities. The amount of money was estimated to about $2 billion. So today, of course, we would like to avoid that. And this is where hydrogen comes into the picture. I will show you in a few minutes that when an engine is unstable, you can inject pure H2 in the chamber and make it stable. You want to be careful because it could also work the other way. Okay, when you inject hydrogen, you may actually go to an unstable engine. So you need to know what you do, but it is again a powerful actuation method for combustion if you're able to use hydrogen as a control method. Now, another question related to hydrogen. Of course, if you have hydrogen, you can say, let me throw out my fossil fuel and replace it completely by hydrogen. But you could also mix H2 and, for example, methane before entering the chamber. That's what we do in the drop-in methods where we add hydrogen into methane lines and we feed it into all kinds of burners. Another method is that you could also inject H2 and your fossil fuel together in the chamber, but not at the same place. And this is exactly the topic of this big ERC project that we are leading at the moment in Toulouse, which is called CERFACS. And in this project, we actually study how you can use H2 to burn fossil fuels more efficiently. So here, the objectives of CERFACS are listed here. Instead of mixing H2 with other gases before combustion, we propose to inject it separately into the combustion chamber in addition to another fossil fuel and to use that to actuate the chamber. We will still burn the fossil fuel, but it will be assisted by additional H2 flames. So what's the context to do that? The context is really, decarbonization of aviation. You know that we need to decrease the amount of CO2 produced by aircraft, even if aircraft with 4 or 5% today are not the first contributor to CO2 production. In the future, there is no doubt we need to do something about it and make it less. Now, there are plans to do that. This is a plan which is shared by a lot of people here. You go from 2010, which is the reference year, to 2050. And you say this is the amount of CO2 which is emitted by the global fleet. And if we don't do something, we go on this line, which is not acceptable. We need to go down to maybe minus 50%. To have an aircraft which produces minus 50% or more than that actually by 2050, we'll need new planes. Okay, there is no doubt on that. And these planes might look like this one. This is a pure H2 plane. And you see here on top of the plane, you got a tank. Why do we need such a big tank? Well, because hydrogen is extremely powerful per kilogram, but not very good per cubic meters. The density is too low. So we'll need cryogenic tanks. And you can imagine, by the way, what it means to have a cryogenic fuel tank on top of an aircraft. Or you need high pressure, but high pressure would be like 700 bars. And you can imagine for the aircraft that this would lead to problems in terms of structure. So, of course, for 2050, we have to do that. But there is an interesting question is, what do we do in the meantime? Okay, because you see on these plans here, if we do nothing, we are still on this line, but we need to be there. Okay, we need to master the amount of CO2 that we do today and the amount of CO2 that we'll do, in 10 years from today. So how do we do that? Well, that's where you have one solution. You have a virus every year, which is not the solution that we would like to have, or you have to find solutions. So one solution would be to equip existing chambers with additional H2 injectors and to use these systems to simplify ignition or facilitate ignition, limit quenching scenarios, especially allow you to run much leaner, because that's one of the reasons why we don't work leaner in those flames is that we absolutely want to avoid quenching. We could also diminish instabilities. And of course, at the same time, we would use this hydrogen that we have. So in CERFACS, we do not plan to fully replace kerosene by H2 today. That's not our goal. But we want to use H2 to burn less kerosene today and in the next years. This will decarbonize aircraft, only partially. Okay, it's not fully going to 100%, but it's doing it, now. And that's an important problem because we need to start tomorrow, not in 50 years. It's also much easier because you need less H2 on board. You don't need this huge aircraft tank that I just showed 5 minutes ago. You could have much smaller tanks. And actually, since you have this H2 on board now, you could also feed the APU with H2 on the airport and produce only water. That would be good for a change, you would not have this smell on airport, and a lot of people would like it. So in terms, of practical aspects, you see that H2 today, or let's say in the years to come, could have very interesting applications for turbines without thinking of this, dream aircrafts which will fly and produce only water. Maybe one day they will fly, okay? But in the meantime, we could go for more realistic solutions. So how would these solutions work? Well, you take here a chamber, which is an existing chamber, actually. That's a French aircraft. And then you feed fossil fuel here, which is kerosene. But then you go to one of these chambers and you introduce hydrogen. Where? Well, anywhere. It's up to you, okay? You can make it steady, you can pulsate it, you can activate it only for ignition or only for very lean zones or only when you have instabilities, and the rest of the time you don't use it, okay? How to do that is fully open to research. It's up to everyone's idea of how you want to use hydrogen. Let me just mention that for the combustion experts in the room, they will certainly say that, whoa, careful, you inject hydrogen here, you will have diffusion flames, and you will make NOx. And that's actually one of the big problems in these technologies, is that if you're not careful in the way you introduce the hydrogen, you will use simulation, you will use situation where you will produce a lot of NOx. And this is where, combustion research is needed again. So let me give you an example of preliminary results that we obtained last year on a chamber which is representative of a gas turbine in which you inject air here and you mix it with CH4 and you burn it in this swirl chamber. So the swirl here is introduced by a swirler, which is here, and this flame looks really, like the flame you would find in a gas turbine engine. And it's fully premixed, as you can see. We have here a mixture of methane and air. Now, if you zoom on the top of the screen, of the top of the chamber here, this is the combustion chamber. This is the injector of CH4 and air, and this is swirling. Remember, so there is a swirl rotation here. And in the middle, you can use this small tube, which has been added, to inject a little bit of H2. When I say a little bit, we will measure how much H2 we inject by comparing the power available due to this H2 compared to the overall power due to H2 to CH4. And the typical levels we use are 1 to 3%. That means that the H2 we will inject here contributes to only 1 to maybe 3% of the total power. So it's really small, but we inject it in a sensitive place, okay? Of course, you could inject it in any other place. It's up to you, you could inject it where you want. It's your problem. And that's where it's actually fun for combustion research. You can imagine the injection type that you want. Now, I will show here an example of a condition where we first will see on the movie the regime where we have only methane air flames. And then in the middle of the movie, you will see that we start injecting H2. You will see that before we inject H2, this flame is quite unstable. It's really not well stabilized. It's not doing well. And when we inject H2, suddenly everything changes and the flame becomes extremely stable. And we use only 2%. So that's extremely small. Okay, so I will just play it again. I know it's not easy to see on the web. So for a combustion expert, what it really means is that when you inject H2 here, at the lip, you promote some kind of small diffusion flame, which actually acts like a pilot flame for the rest of the system. But it fixes your problem, okay? Because now once you inject the H2, you can have a stable flame, and then you can operate your engine at this position. You can actually look at this operating map here, where you plot the flow rate on this axis and the occurrence ratio on the other axis. For people doing engines, that's a classical result, and you can add here as a size of this circles here correspond to the noise which is emitted. So here you see, for example, for these points, you have oscillations of the order of 1000 Pascal, which is, quite unstable. And you see that this is a typical gas turbine plot. Means, yeah, there are cases where you cannot go. For example, these 4 points here, don't even go there because everything will explode. Here it will make a lot of noise. And these points here, where they look okay, you can operate things here. But you see that there are many places when you cannot go, especially, if you want to go very lean here, or if you want to go to a very small power, this chamber will oscillate. So that's the map without H2 injection. So we did the map now with H2 injection. And you see that when you go to H2 injection, everything changes. All these points here, which were unstable before, look at the map before, that's the new map. All these points have become stable. There are still unstable points, but those are high power. So high power is not where we want to go. We are really interested in this zone here, and now we can operate here with only a little bit of addition of H2. We can operate all the points and still be very stable. So that's quite promising, and you could actually, we haven't done it. What we want to go is to go here, to go leaner. Now that you're stable, you could even go to places where you put even less fuel, and that's what you want if you want to save kerosene. Now, if you want to be more quantitative here, we saw that the direct H2 injection of a very small amount of H2 is enough to stabilize the flame. And we can run the experiment in linear condition. We can consume less fossil fuel. Here it was methane. So decarbonization is partial, but it works, and you can make it work. Now it's not that complicated to do. You don't need to build this monster aircraft with H2 tanks everywhere. Now, we know also that on this system, injecting H2 at the place we did works better than injecting methane at the same place. And again, for those of you who do kinetics, it's easy to understand. It's because, H2 burns much faster. And even if you inject CH4 in the center of the device, CH4 is just too slow to help stabilization. It also works better than mixing H2 with CH4 before entering the chamber. We know it's like this because we tried, We tried this configuration here on the left, which was the reference case where you have no injection at all. The first one we did was injecting H2, that's the result I've shown you, which works. Then we tried to injecting CH4 at the same place instead of hydrogen. And you will see that this one does not work. And then we tried to inject H2 here in the premixing passages. And so when you inject the CH4 instead of the H2, you see that the map is almost the same. You cannot stabilize these points. You're still stuck with very unstable points here. And when you inject H2 and you premix it with CH4, this is what you obtain. Same thing, the map is changing a little bit, but not much. So it really proves that what you want to have in this system is an injection here of H2 directly in the chamber. And that's very different to do that, for example, than what you would have if you inject the same H2 in the premixing passages. So it really suggests that injecting H2 by premixing it is not necessarily the best way. If you want to do things to your flame, you have to inject H2 directly into the chamber. Let me say also that we measure NOx in these systems, and that these solutions increases NOx a little bit, but really not much. So it could be a practical system to industrialize. Okay. I want to finish now by mentioning something. I know that many of you, especially the young guys, are doing CFD. And of course, the point which comes out right away is, can we compute these flames here? Now, what you need to realize is that when H2 is mixed, for example, with methane, and after that you inject it into the burner, you can view the mixing of the two gases as a new gas, which has its own flame speed, its own autoignition terms, etc. And then you can apply your usual tools to this new fuel. So it's not a big deal to do CFD of an H2CH4 flame if you premix everything. I'm sure you can adapt even commercial codes to do that. It's not that tough. But if you inject H2 separately, as we propose, into the chamber, the problem becomes much more complicated and interesting for the CFD folks, because now we have actually in this system, we can have two flames at the same time. One flame of CH4 air, one flame of H2 air. And you have to model all of them at the same time. And this is where things get interesting. As you know, H2, we said already, is extremely fast. So H2 will create diffusion flames in many cases, while CH4 is premixed, so it will lead to premixed flames. So now we need models which can address two fuels at the same time and two types of regimes at the same time, a partially premixed flame on one side and a diffusion flame on the other side. So let me give you an example. Okay, this is if you look on the web, for turbulent premixed flames stabilized behind flame holders like this one, you will find billions of papers. Okay, so for example, you have a lean air CH4 flame here, and you will find PDF model, flamelet models, you name it. I mean, you can have everything you want here. But suppose now that in the same code I add an injection of hydrogen into the burn gases. Now, first, it will be a complicated flame because vitiation of the air here, which is burning with H2, is complicated. It will be a mix of O2 and burn gases at high temperature. And obviously, it will certainly be a diffusion flame. You may actually have autoignition in a system like this. So if you need now one single code to model all that, well, good luck, okay? It's gonna be interesting. It's not only having a kinetic scheme which can do hydrogen and CH4, which is already an interesting problem, but you need to do at the same time premixed flames and turbulent diffusion flames. Now, this is still an easy situation because I've put my turbulent flame before and my diffusion flame afterwards. But now, in many cases, what we'll do is a little bit different. That's actually what's happening in the experiment I've shown. The H2 injection is right at the place where the premixed flame is located. So now we have an interacting premixed flame with a diffusion flame, and everything, of course, will mix, because the H2 injected here will also modify the chemistry of the premixed CH4 flame, because the CH4 flame also produces H2. So it will be a very nice mess. And in terms of physics and in terms of science, I believe it opens quite a very, let's say, a very exciting topic here. We will need DNS of such flames, and then we will need a larger dissimulation of those flames. And I'm sure that this will keep us busy for a while. Okay, so to conclude now, I believe that hydrogen may become a key factor in the energy mix of the world. And I believe also that we should not limit ourselves to just put hydrogen and mix it with fossil fuels. Okay, that's the way it's done today. That's the famous drop-in method where you just add hydrogen into methane, for example. It's not the only way to use hydrogen. It's probably not a very intelligent way. You will also have noticed that it's also a great opportunity for the combustion community now, because since this might be a solution to the problem of energy storage, H2 combustion might actually become the solution instead of combustion being the problem, which is what we hear every day those days. And of course, to conclude, to do all that, there will be a need for a lot of fundamental science. So it's a very nice opportunity for this community to do something which will be combustion, which we know how to do, but something which will be also useful for the community and hopefully for the world. Okay, that's all I wanted to say. I will stop here, and if you have questions, I'm ready to answer. Thank you.
Okay, good. Very wonderful talk. Thank you so much. So let's move on to question session. We received a lot of questions actually, but for audience, we cannot ask all the questions from audience because limited time. So we are sorry about that. So I collect the question and I can share my screen with the question. Okay, good. Can you see my question?
Yeah.
Yeah, okay. The first question is from Dr. Asa Box from DLR. And his question is about the about hydrogen in the machine flame. It's a volume fraction or mass fraction?
Yeah, it depends on the configuration. I'm sure Isaac knows the answer to that. Huh? I think it depends on the configuration. But in practice, I think in most cases, people talk about mass. But I would need to check. I think it depends on the case. If you talk about the countries where they use drop-in and they just use they introduce H2 into CH4, I think it remains pretty low in any case, you know, because afterwards you get flashback, you get problems. I would need to check the exact definition. Good point, Isaac.
Okay, thanks. The second question is from Paul from CFD Research Corporation, and his question is, several mechanisms of combustion instability are now known as today, along with the partial control strategy. And thank you to a gradient extent to your work. Where do you think are the most ground challenge for hydrogen emissions? Injector design, flashback. Can you please give some comments on the current work you are conducting on these aspects?
Well, that's a big question, but the only thing I can say is that in the field of power gas turbines, people have already moved to hydrogen. And I think moving to hydrogen is not too difficult when you put not too much hydrogen. The last part of it is when you go, you know, from 80% hydrogen to 100% hydrogen. This is where things get really complicated. And I don't think we can predict today how these things will change. We have quite a few examples where flames get crazy when you go to 100% hydrogen. And I know that most gas turbine manufacturers are actually just trying to build those engines with hydrogen injection. And the whole question is, what is the hydrogen injector? What do you do at the level, at the place where you were injecting kerosene? You remove that and you put something else at its place. So what do you put there? And I think that's the main grand challenge, is to design H2 injection systems, which might, in the best world, be able to handle both kerosene for certain regimes and maybe go to pure hydrogen for other regimes. That's a very, very stimulating question. I don't have the answer.
Okay, good. And the next question is from Tom. And his question is regarding adding hydrogen to reduced instabilities. Does that counteract the intention of lean flame being a low NOx solution?
Yeah, absolutely. That's a usual compromise. In most gas turbines, you have to choose between instabilities and low NOx. And it's difficult to ensure both. In most cases, you have, it's a compromise. And clearly, these two objectives go against each other, because when you use H2, usually you introduce diffusion flames, and that increases NOx. Again, that's one of the big challenges. How do you use H2 to reduce instabilities without making more NOx? That's going to be a big problem.
Okay, thanks. Next question is from Professor Hailin, and his question is about detecting hydrogen leakage is very important in hydrogen safety. What's the best sensor in detecting hydrogen leakage or measure hydrogen concentration?
Yeah. Okay, that's not a question for me. It's a question for experimentalists. But I would say I know of a very bad way of detecting hydrogen is that when it makes boom, it's too late. Okay, so that's what we want to avoid. Now, in terms of experimental techniques, yeah, I'm sure that this will belong to what people will need to do. They will need to deploy sensors to detect hydrogen. There are already, sensors like this in every lab doing combustion has sensors for hydrogen. So actually, if you have sensors for CO, for example, they detect also hydrogen. So I'm sure there will be many optical systems to do that. But I cannot give you a clear recommendation now.
Thanks. So next question is from Professor Li Chao from Purdue. Her question is regarding use of hydrogen, which is produced from renewable source. How will combustion engines compete with fuel cells?
Well, it's the equation is simple. I was talking to a friend recently in a car company. He was telling me, you take a fuel cell, you have an efficiency of 60 to 65% and a cost of 12,000 euros to make the engine. And if you take a piston engine, you have an efficiency which might go up to 50%. if we deploy, you know, the best combustion devices we can have, and the cost is like 2,000 euros. So now it's not a combustion problem anymore, it's an economical problem. Do you want, you know, is it worse to increase the price of the engine by a factor of 6 to 10 to gain 10% in efficiency? It's the companies will make their choices, I'm sure.
Good. Next question is from Professor Katerina. Her question is about your research. Would this plan be able to dock at the present airport, or do we need different stations to? How about storage at airports and filling? When would one have to start planning? Are this question also addressed?
Yeah, well, we had a meeting, a very interesting meeting recently in Toulouse, where we had people from aircraft companies and people from rocket companies. And the people from aircraft companies were saying, we're going to build an aircraft burning H2. And the people from the rocket companies were telling them, good luck, you know, because they want to do it cryogenic, okay? Cryogenic, if you imagine cryogenic, what you do in a plane, in a rocket, which is cryogenic, is that you release the hydrogen when the temperature gets too high. So you get those fumes of hydrogen going on top of the rocket. Now imagine an airport where you would have 100 aircraft, you know, exhaling H2. That's impossible. You cannot do that. Anyone smoking there and you get a big catastrophe. So this is why we believe that the amount of hydrogen that we put in an aircraft for the next 10 or 20 years will have to be limited. You know, small tanks, high pressure tanks, but small tanks, not these huge monsters. Because in terms of how can we use full H2 aircraft for the future, this is an unsolved problem. It's a crazy problem. Not for combustion people, but for safety people, yeah. I agree. It's going to be interesting.
So next question is from Professor Xiaoyu. His question is, how does the hydrogen injection method compared with other methods in stabilizing machine flame, such as acoustic wave and plasma, in the aspects of performance, emissions, and energy consumption?
Yeah, anything I've shown here with H2, you can also do with plasma, for example. And again, then it really comes to what's the practical aspect when you put that on a plane. For example, in planes today or in helicopters, they would argue that it might be easier to use plasma because they already have all the electric system on board, while introducing H2 might require an additional tank, an additional line, etc., and an additional control system. So plasma is definitely another good way to reach the same objective. I agree.
Thanks. So next question is from Dr. Ivan from TU Delft. You mentioned that NOx slightly increased in the case where hydrogen is burned as pellet. Is there any observed change in the overall CO production as well in respect to baseline case?
Yeah, we didn't see an effect on the CO. Those flames are burning, you know, very efficiently, and they are lean, so we don't do a lot of CO anyway. So we didn't see an effect on CO.
So we still receive some questions on the chat channel, and we also have some time for more questions. And so the next question is from MHB, and he would like to ask how hydrogen-assisted combustion can affect the instability of combustion systems.
Well, we know that combustion instabilities are really due to a lock-in resonant phenomenon between the flame and the acoustics. And so what controls combustion instabilities is a flame time of the flame itself. And when you add hydrogen, you change this flame characteristic time. So there is absolutely no doubt that when you change the H2 content in the flame, you change the characteristic time of the flame. You make it shorter or longer, and then it can lock in onto another mode or not. So it's just another way of changing the resonant phenomena between the flame and the acoustic waves. But it may not go in the right direction, okay? We know cases where you inject hydrogen and the flame gets more unstable.
Thanks. So it seems that Dr. Isabox proposed another question. It is clear that modeling multi-regime, multi-field flame will be challenged. what might be the solution? How might one approach this challenge?
Can you repeat? This question is on the chat. I didn't see it.
It's Xbox. I think it's the fifth one from bottom. It is clear that modeling multi-regime, multi-field flame will be challenged. What might be?
Yeah, sure. It's really a CFD problem. There are two steps there. The first step is relatively easy. It's to create kinetic models which can handle hydrogen and other fuels. But in practice, most schemes for heavy hydrocarbons include already H2 into the scheme. So that should not be too difficult. The main difficulty is really the turbulent combustion models, which will not know if you have premix flames or diffusion flames or a mixture of the two. And that's where things are going to be complicated. So it's really a work for the turbulent combustion people.
Next question is from Taraj. His question is regarding the estimation of CO2 reduction when using hydrogen injection.
Sure. The idea when you use H2 in those flames is that first, for the H2 itself, you replace the combustion of a fossil fuel. So you will produce more water and less CO2. And the other thing is that if you're able to run the combustor in leaner conditions, you might even be able to further decrease the amount of CH4 or fossil fuel that you increase. So you can have, 5, 10, 20% of reduction of CO2 just because you reduce the C that you inject in your system.
Thanks. Next question is from Bing Yang. He noticed the quenching problem in your slides. Do you mean the extinction of flame quenching by the wall?
I was talking about the global extinction. In many systems, when you get too lean, the flame just blows out, and that was my objective. Yeah, global quenching.
Thanks. Next question is from Dr. Lu Tian. And do you think transport PDF method can be used to tackle the multi-regime simulation of turbulent combustion?
Yeah, well, actually, it's interesting because the PDF method has not been very successful for premix flames because they were flamelet models, and same thing for diffusion flames because you had alternative methods, but these methods could handle only one regime at one time. Well, the PDF method should be able to handle all regimes. So I believe that there is a path here, yeah, for reintroducing PDF methods into these problems. Yeah, absolutely.
Thanks. Next question is from Tom, and he wants to know, do you consider adding additional hydrogen into the liquid fuel?
Yeah, that's the thing, yeah, because I cheated a little bit. I've shown you H2 mixed with CH4, but in a real engine, we would have to mix H2 with kerosene. Honestly, I don't know. I think it's, I think we need to do it, okay? We need to check it out. I don't know. Normally on the paper, if you have a flame working with kerosene and air and it's burning, you could have additional H2 injection anywhere. So it should be okay. It will be difficult to model, but it should be fine experimentally. We haven't done it yet.
Thanks. Next question is about ammonia. Can you give some comments about ammonia as a hydrogen carrier rather than using pure hydrogen?
Yeah, a lot of people again are trying to use ammonia.
Yes.
What's also very interesting for us is that we go on the opposite side of H2. Okay, H2 is burning too fast, ammonia is burning too slowly. So that means that we will need to redesign the engines anyway. What could be very exciting actually is to mix ammonia with some H2 again. Okay, you have to use pilot flames driven by H2 to force the ammonia to burn. So that again is a very nice field of investigation for combustion people.
Thanks. Next question is from Toshiro, and he wants to know how you can consider whether hydrogen blended fuel or biofuel is realistic.
Yeah, well, biofuel is the alternative method for a hydrogen. Okay, at the moment, if you go to most companies, they will tell you they investigate hydrogen and biofuels. So you could even imagine mixing the two. At the moment, I don't know, but clearly the biofuel is something I did not discuss at all today, but it's the other solution to our problem of decarbonization of combustion.
Oh, thank you very much, Terry. This is very exciting and very informative and a new direction, I believe. And I have one question before I congratulate you. Is there any way that you can, using electricity, that can pyrolysis that some kind of hydrocarbons on board and separate carbon and then burn hydrogen directly? So in that way that you reduce the possibility to have a very heavy tank.
Yeah, exactly. I know that actually people are thinking about that to do the hydrogen on board and not have to carry it, which would be probably, that would be a smart way. You have to do a balance, I guess, in terms of you would need electricity. And to get this electricity, you would need to burn more kerosene. But it's a global balance again. But that would solve the problem of the H2 tanks, I agree. But at the same time, you know, H2 tanks, you can buy a Toyota Mirai today, and it has 700 bar tanks on board, which you could carry on a plane. So again, this is really something that has to be investigated by companies, and I'm sure they're looking at this. Yeah.
Terry, thank you very much, and for the great talk. And everybody, please turn on your video so that I just say a few say some greetings to each other.